All right, I see I got a few of you out there. What questions do you have for me today? Yeah, that was a little greedy. So just a reminder, the live streams aren't lectures. They're more office hours. So I don't really have anything prepared for any of these live streams. It's mostly just what questions do you have. So I've got the chat window up here on the left. I'm also going to be kind of messing with making some inductors and transformers right now. So curious, that's why I've got the glasses on so I can see what I'm doing. But I've got the chat up, so if you've got any questions, just feel free to ask them. And yeah. Can we go over the frost circles using the cyclopentatriene compound example from the PowerPoint? All right, give me just a minute to bring up that example. Let's see here. Cyclo octa triene. Cycloocta tetratriene. Okay. So for the frost circle, this is used to approximate what we would generate if we did molecular orbital theory. In molecular orbital theory, this is the adding and subtracting of wave functions. Fortunately, none of that shows up in Lewis theory. So the frost circle here is a really crude approximation of what molecular orbital would predict, molecular orbital theory would predict for where these electrons are in the pi systems. So for the frost circle, we're always going to have our lowest energy orbital at the bottom of the circle. We're going to count up the number of pi orbitals and lone pairs that are used to generate the conjugated pi system. So we have 1, 2, 3, 4 pi bonds. So we have 1, 2, 3, 4 molecular orbitals that will contain these conjugated pi electrons. So the way I remember it, for every pi bond you plan on using and every lone pair or vacant p orbital you plan on using, that's going to be the sides of a polygon. So if we have 3, we're going to have a triangle. If we're going to have 4, we're going to have a square. If we have 5, we're going to have a pentagram. But always with one corner pointing down. And that's going to predict where things are in the frost diagram. Now, the next thing we do for the frost diagram is that we count the number of electrons in the pi orbitals. So we have 2, 4, 6, 8. So we have 1, 2, 3, 4, 5, 6, 7, wait. Is that correct? Yeah. So we have 8 electrons. Now, the big thing with aromatic systems is we can't have non-bonding electrons. So the midpoint of this circle, everything below it is a bonding orbital. Everything above it is an anti-bonding orbital. So if we have anything in non-bonding orbitals, or the potential to put anything in non-bonding orbitals, this ends up being not an aromatic system. And the reason being is that a non-bonding orbital means the electrons were actually just as stable sitting inside the p orbitals as they would be if we ended up making all these bonds. Again, this is really hand-wavy. It's because we're trying to apply molecular orbital theory to something that doesn't use molecular orbitals at all. Lewis theory doesn't use molecular orbitals. But if we do end up with a situation where we have electrons in these non-bonding orbitals, it ends up being not aromatic. And actually the Frost diagram, your book really emphasizes it for some reason. This is where we get the 4n+2 rule. So if we ever have 4n+2 electrons in our conjugated pi systems, we are guaranteed not to have any electrons in non-bonding orbitals. So Frost diagram kind of makes that collapse out. The more useful thing here is that 4n+2. I know it's different from the slide. Let me open up the slide then. All right, let me actually bring up the PowerPoint. I will also give you the full disclosure, these like frost circles like never come up in practice. So if you're curious why I'm really rusty on it, but I can do the aromaticity rules really fast, it's because the frost diagrams really are not that useful. Come on, you can do it. All right, what's the easiest way to determine aromaticity? Aromaticity, yes, it's going to be on the test. You have to determine if a compound's aromatic. And actually, the discussion board next week, that's what the question is. It gives you a list of compounds and asks you to determine which ones are aromatic. Oh, sorry, it's not for. I was curious why this ended up with so many. Oh, I'm sorry, it's not for every pi bond, it's for every p orbital used. That's why I ended up with so many. No, the slides are correct. This is what I get for trying to do it from memory. So you get an orbital for every orbital that's used in generating the, yeah, I should have known that. You draw a line for every orbital that is used to generate the conjugated pi system. So we have 1, 2, 3, 4, 5, 6, 7, 8 p orbitals. The reason I should have known that is if I just have one, I should end up with a bonding and antibonding. Okay, so we actually have 8. It's an octagon sitting on a corner. We count the electrons, 1, 2, 3, 4, 5, 6, 7, 8. We still end up with 2 electrons in the non-bonding orbitals. Did I discuss it? No. So this would still be a non-aromatic compound because you end up with electrons in the non-bonding. But yeah, it's twice as many orbitals. Yeah, you can also memorize the pattern too, 2, 6, 10, 2, 6, 10, 14. Honestly, aromatic systems don't get bigger than that. 4n+2 rule is nice, but yeah, if you just want to memorize that sequence, you're not going to be wrong. The other thing is that aromaticity is kind of this funny thing when the molecules end up being really big. So we talk about compounds being aromatic, but what we don't discuss is like when parts of a molecule are aromatic. Review your discussion board post. Well, let me find it. Oh, thank goodness, you're the first section I opened. Okay. I agree with your one for the 2-methylheptane. The 6-methylheptane, a terminal radical isn't nearly as stable as a secondary radical, so you might want to go check that one out. So that's the 6-methyl-2-heptene. I agree with your answer for the 6-methyl-3-heptene. And I would check your answer for the 6-chloro-6-methyl-2,4-heptadiene. That's another one that the terminal radical is not the most stable one. And I agree with your synthetic route. Like, it's a pretty straightforward synthesis. So we're going to treat these like these are molecular orbitals, and if electrons have degenerate orbitals, meaning that they have the same energy, they would prefer to unpair. So in this case, it would look like we have two unpaired electrons in these antibonding orbitals. Now, that said, this is not an accurate picture at all of how aromatic systems look. So it's not important that we ended up with unpaired electrons so much as we end up with electrons in non-bonding orbitals. The reality is that based on the symmetry, you would actually end up getting 1 here, 3 here, and so forth. So neither terminal radicals or terminal alkenes are stable relative to their non-terminated forms. So a secondary and tertiary radical is more stable. A double bond that's connected to a whole bunch of other groups is a lot more stable than a terminal alkene, and that's actually the reactivity of terminal alkenes is what makes them super easy to separate out. I'm sorry, I got off track. So with this, understand that this is just an approximation. It is not accurate at all. The inorganic chemist in me really cringes seeing this because it's really glossing over a lot of details, and this isn't even the shape of the orbital. This isn't even the shape of the energy diagram. But that said, it's not important. What we're trying to show when we do this is if we expect electrons to end up in non-bonding or if we expect electrons to end up in antibonding orbitals with our aromatic systems. But yeah, this is not representative of all of what the molecular orbital structure looks like for any of these compounds. It's just an approximation to determine if we have non-bonding electrons or antibonding. So if we end up, just bring back to this idea of the terminal alkenes, if we do some type of free radical halogenation, we can halogenate at 2 points in this molecule here and here, and both points will be resonance stabilized by this double bond flipping back and forth. The thing is that a radical here is not as stable as a radical here. We do expect all products. In fact, you can work out a whole distribution of products from this. So if I substitute here, I could get resonance stabilization to do this. I can substitute here. If I do the free radical here, I can resonance stabilize to put the radical here and end up getting basically the coloring on a whole bunch of points. The idea here is more what's the most likely product. So the kinetic product, the one that you're expected to form if you get no resonance, the one that's most stable is the one that puts the radical here. It would be resonance stabilized, which would make that free radical more stable. But we're going to focus more here on the kinetic product. So let's say that you didn't get the radical moving around. What would you expect to be the most stable radical position? So yeah, I would say your answers to the second and fourth need changing, but it's not, you are correct. Those products are formed. I mean, they are there. They're just not there. We're looking for the major product, the one that's formed the most. Yeah, and even then, that's a misnomer. It's not really the thermodynamic product. It's just the one that's accessible at higher temperatures. So for simplicity, let's just stick to the kinetic product. So, really need to put this back. So for the anion versus cation forms of cyclopropane, we've got three orbitals that are used. So we've got 1, 2, 3, 1 on each carbon. And then I have to count the number of electrons that are here. Well, I get 2 from the pi bond. And then since I'm using this carbon, the p orbital that, there is a p orbital that contains these 2 electrons. That's where the 2 other electrons come from. So this gives us a total of 4 electrons in this molecule. For this one, we still have the 3 p orbitals. So we get 2 from the pi bond, but we don't get any from that p orbital that contains that cation charge. So that's where the 4 comes from here, is that the reason we have a p orbital available for bonding with this compound is because of this negative charge. It's a p orbital that contains electrons. Give me just a minute. Let me see what that doorbell was about. I'll be right back. All right, just package. Oh, really? What other questions you got for me? So the p orbital on the top carbon is where we contain the charge. So if we have positive, we don't have any electrons. If we have a negative, we have 2 electrons. So on the right side, it's a positive because we don't have any electrons in the p orbital. So the p orbital is still participating in the aromaticity. It doesn't contribute any electrons to it. If you're going to use that p orbital to create aromaticity, you have to use the electrons that it's in it. So the reason why we can create a conjugated system here is that we have a p orbital available. It's just that that p orbital also contains electrons. And since it contains electrons, it has to go into our electron count. Have to count. Particularly if you have something like an alkyne where you've got the 2 pi bonds, only one of those pi bonds counts. So it has to be in plane. Yeah, so I would agree with what you got posted for the discussion board here. So your new discussion board post, I would agree with what you put in there. And as for sp3 counting for conjugation, it can. If you have something like an alkyne, though, there's actually 2 pi orbitals. You can only use one of them. Okay, you're welcome. And the intermolecular forces of aromatics, it's interesting. Honestly, there's not that much on it. They do interact a lot more than you would expect them to because of that pi stacking, but your book doesn't seem to talk about it that much. And honestly, I only know about it from theoretical work I did while I was in grad school, so I can totally see why the book doesn't care that much about it. It's kind of an esoteric topic. Basicity. Oh, don't tell me that's another one where it's a weird question. Oh, so it has to do with resonance stabilization. So in order to be a base, you have to be able to accept, you have to have lone pairs available for bonding. So when you look at these compounds, the question is which of these forms a... Oh, actually you kind of already know this. So it's actually kind of more Orgo 1 review. I don't want to say this without ruining it. Well, I guess I can give away the answer. So you know alcohols can deprotonate. That's what gives rise to that bending mode at 3600 in the IR. So alcohols are basic because they accept hydrogens. They have lone pairs that are... okay, hold on. I think I see how this is meaning for you to answer it. So in order for this to be a base, you have to have lone pairs to accept electrons. Now the CH bond itself is pretty strong, so it makes sense that toluene minus the hydrogen is the strongest base. But even then, if you look at the oxygen and the nitrogen, even if they that negative charge there is stabilized by resonance. So, sorry, I see the answer. I'm just trying to figure out how to explain it. Well, I'm sorry, I know the answer. I'm just trying to figure out how to explain it. Because it's kind of Chem Orgo 1 review. Methyl groups don't give up hydrogens. They're not acidic. So the other way to look at it is that which of them is a better acid? Alcohols give up hydrogens all the time. That's what gives rise to your bending mode at 3600. And amines are kind of the same way. They have that bending mode. But I'm also trying to think about how you would explain this in terms of resonance stabilization, because it's also a matter of how well they resonate with the ring. Yeah, sorry. There's better ways to answer it other than the resonance, but I can see what it's getting at with the resonance argument. I decided this year I want to build my own radio. It's actually been a ton of fun, like getting back into soldering. Oh, good. Glad to help. See it helped. I'm annoyed that we use the trade names. There's no way to derive the trade names, but I also kind of get like these trade names have been around for a very, very long time. And with aromatic compounds, we're not going to go nuts on the naming. You can. There's definitely, I've seen instructors that put like all 6 positions are substituted. We're getting ready to get to the dirty secret of organic chemistry. The IUPAC rules are nice. They die when the molecules start branching their way towards biological. So we're not going to worry too much about naming beyond simple aromatic compounds. And I mean simple meaning up to 3 substitutions, possibly 4. But things where you've got 2 rings and they're substituted, it's not worth it. Other questions? They're later than that. It's about how to name aromatic structures. So you'll get the OMP, orthometapara naming, for when you have 2 substituents that are the relative to each other. And then there's also the traditional numbering where you just name it and you just take the highest priority group and use that as the starting position. But that's definitely later in the notes. And naming aromatic compounds, the bigger thing is just learning all the little trade names, because there are like toluene, aniline, benzophenone. Those kind of are intuitive to what those mean, but honestly, not really. But you have to know them just because they do show up a lot in, like even in your lab manual, it'll use benzophenone. But definitely last semester we didn't cover naming aromatic compounds. You were exposed to some aromatic compounds, but we didn't formally learn how to name them. Yeah, that's kind of what you have to do is just kind of memorize them. This is an unfortunate thing about aromatic compounds is that we knew about them long before we knew their structures. We had the IUPAC system going. You can name them, but things like methylbenzene, it's toluene. Anisole, styrene, these are all ones that we knew what they were. Polystyrene, it's just a polymerized version of styrene. We knew what the compound, we worked with the compound and worked with it long before we actually knew what it was. But because of that, we're also burdened with these non-intuitive naming systems. Like toluenes, methylbenzene. Hey, Brittany. Yeah, take your time on this. Like aromatics are a lot. Like you don't need to do it all in 1 week. And the reactions of aromatic compounds, they are very interesting. Um, I find them personally the most interesting part of the aromatic chemistry. You're actually going to do a synthesis. Your second lab is the synthesis of an organic compound. You're going to get to make the aqua regia, the really, really nasty stuff. Which I'm shocked they even let us do a nitration reaction. I mean, it's pretty aggressive stuff, but it is cool. Other questions out there? So for those of you who are trying to go ahead, the two big things about the reactions with the aromatic compounds that make them challenging. One, just memorizing what they do. The second is that they tend to change how the next thing gets added. So if you take a benzene ring and you start adding things to it, it matters the order that you add them in. So we have what are called directing groups. They're called what are called directing groups. So they will direct the next addition to the benzene ring, and they can direct them ortho para if they're typically electron, if they're also activating. If they're electron withdrawing, then it tends to be a meta director. Now, as with all things organic chemistry synthetic related, you're going to get a witch's brew of everything. What we're trying to do is we're trying to put the odds in our favor when we do when we're starting to add to this ring. But not only do you have to memorize what the things do, you have to memorize what impact they have on the next thing that gets added to the ring. For the situation where we have to try and get the chlorine on the most substitute correct carbon. Generally speaking, yes, that's what you're going to end up with. The thing is that the alkenes are going to create resonance stabilization. So resonance stabilized positions are better than more substitute. So a secondary carbon will become more stable than a tertiary carbon if that secondary carbon is near an alkene. So that's more what it's getting you at is just for an alkane, no double bonds, yes, most substitute carbon is going to be the one it reacts with. Once you start introducing those double bonds, it's the atoms nearest the double bonds that are going to be the more stable positions due to resonance stabilization. All right, we're coming up on the end of the live stream. So any questions you have, feel free to email them in advance or show up to the live streams. No live stream Monday, but there is live streams Tuesday, Wednesday, Thursday, and Fridays. Any other questions before we head out? You're welcome.